in my mind, there's a little teaching philosophy that's going on that kind of has to do with words per minute, and the words per minute that you think versus words per minute that you speak. And this is why you guys get so bored in some of these lectures, is because your brain's clicking along at, I don't know how they come up with these numbers, but they're clicking along at 800 to 1,000 words per minute, but I can only speak at 100 to 150 words per minute. So your brain fills in, right? Your brain's looking at other pictures, your brain's thinking about, what your dog is doing, or, who knows, but it fills in lots of things around the subject matter, and periodically it comes back and pays attention. So to me, the key is not so much how much I say. The key to effectiveness is not even how much you do. My goal is that, like, and how I teach this is 6 months from now, what did you retain that's still useful? And so the key to retention is to struggle and make you think. So what you're going to see is very, very little cookbook stuff. The labs that you may have gone to before, they kind of say, here's a piece of equipment, here's step 1 through step 17. I can think of one place in this whole curriculum, and that's when we're hooking up mechanics to motors, where I actually have a step-by-step, do this in order, or you're going to break all my equipment in two. All the rest of everything we're doing is, I'm going to give you a problem to solve, and I'll help fill in around it, and I'll lecture on how, the key pieces. But in general, you're going to have to work through and figure out how to solve a problem. In 6 months, or not even that long, a bunch of you are going to go to work. And as engineers, it's almost never that the guy from marketing or your customer or your boss comes over with this predefined set of do this, this, and this, or here's even the specs you're supposed to hit. They never do that. They come with the problem, and you're the engineer, and you have to sit there and figure out and gather information about the problem itself. So that's what I do. I'm going to ask you to design from data sheets instead of from equipment that's in front of you. And that's a little bit harder because partly I want to get you used to reading data sheets. I want you to get you used to processing numbers, processing tolerances and conditions that they might have done when they printed a tolerance. But in the real world, most of the things you design, you don't get the equipment first. You design it and analyze it, and then order the equipment that you think will actually work after you've finished your analysis. I mean, think about almost all your classes at Chico State, and they are, in engineering at least, there's lots and lots of people outside of engineering that can build things. Things obviously get built all the time. So the whole point of engineering is for you guys to design it, but do enough design work to be able to predict what's going to happen when you build it. And so if you look at all your classes, they're all designed around designing it enough and then analyzing that design. What's going to happen when you build it? And in mechatronics, that's not so much the FEA stuff. It's much more of a, how much torque do I need, predicting the wiring diagrams, writing not predictive code, writing sample algorithm, testing them out to see if the code is likely to work, and how. So you're going to be designing from data sheets, and that's difficult, but that's the way it is. And some of them are available here, some of them you'll have to go online and get. Mechatronics is an awful lot of concept material coming from different, mechanical, electrical, software, controls, and it's individually, it's all pretty assimilatable. But for some reason in this class, when you start bringing these concepts together and you have things happening on your desktop and you not sure what it was, the interaction between these things gets really complicated. And so I'll help you break it down, but that's it's one of the funnest things about it is what's going on. There's all these things interacting. The complexity is really kind of exponential, not just additive of these different technologies. So some of the things, I'm going to start writing some things down that I kind of expect that we're going to need to do. Let's see, expect. Oh, I know what else I was going to tell you. By the way, there's no PowerPoint here. So lectures will be recorded, obviously, and you can watch them later. I think that'll end up happening quite a bit. I really appreciate so many of you guys turning on your cameras. And that helps, obviously. But part of the PowerPoint is really boring, back to that words per minute thing. You know, you read it through and then you wait for the professor to talk it through and it doesn't work. So I don't do it that way. I do it very much more whiteboard style. And I come at this in a way because I've done, you know, from feedback, but also way back when I did a seminar, used to do motion control seminars for industry. And you'd have, one time we were doing it for Hewlett Packard up in Corvallis, and they had like 40 of their engineers attending. And I'm this, I don't know, I was probably you guys plus 3 years, maybe 4 years, right? And I'm teaching other senior engineers about motion control. And you could get away with that then because there wasn't that many people that actually knew what motion control even was. And so we had a set of slides. It wasn't PowerPoint, it was the actual slides, but we had a set of slides. And they didn't come in. And so I'm sitting there staring at these 40 engineers and my slides are not there. It's like my PowerPoint file is gone. You know that feeling, right? When it's like, well, now what are we gonna do? So I turned around and saw a whiteboard and grabbed a pen and just started lecturing. And I'd never really done it before, but you know, just draw. I knew the pictures, I knew the content, I knew what to draw, and so I started lecturing. And the feedback was that was so much better. I mean, they were gushing almost about, oh my gosh, that, you know, it was interesting, and it wasn't necessarily me, but it was more of what they were used to, which is slides versus engineers really learning engineering. And it was at a pace that their brain worked. So that kind of stuck with me. And that's why you'll still see whiteboard and writing it down and that kind of stuff. Think, then do. You know, you've heard learn by doing, but to me, learn by doing isn't what you want. You want to have to think, and maybe even right here is the struggle. And that's struggling with your brain, trying to figure out how does this work? How do these things work together? And then once you do it, then you get it. And it's a pretty cool feeling too when that happens. To me, that's one thing I'm going to expect you to do is think. Now, in lab setting, normally, if we were just in a big group of 40, it's almost impossible to do it in lab. So this is actually where virtual learning is going to fit this class kind of good, because you're going to be able to sit and look at what you have in front of you and be by yourself with your brain and think. And you can't do that in lab. In lab, it's, you know, you can really only just come into a lab with a preset of stuff and do it. I had a experience one time where we did all the design and installed a set of 4 servo gear motors for a telescope. But this is one of those telescopes that's on the top of a mountain in Hawaii, where the whole dome, you know, the dome is the size of, I I don't know, the church south of town, and the whole dome turns and it's on this huge thing. You know, we did all sizing, installed the motors, and then it's time to go in and program it and do some of that kind of stuff. But it was at 13,000 feet. And the engineers that they didn't like my rate for how much I wanted to charge to go out there. So they had just a couple of our engineers come out because they charged a lot less. And they would have to go up there, and they couldn't actually think at 13,000 feet. It just didn't work. And I equate that to like being in lab. There's too many distractions, you can't think. So they would actually have to come back down to sea level with all their notes, process it, think through, make a list of what they wanted to do next, and then up the mountain they would go, and they would read that and just do what it said verbatim without being able to think much about it, because they said they just couldn't think. It was an odd phenomenon. They weren't prepared for that. And it's the same way of coming into lab. When you come into lab with a whole bunch of people, you can just do what you planned, and that's about it. But truly understanding when something goes wrong, wow, what happened? You can't figure it out. So this virtual and getting you equipment is gonna actually work pretty good for you actually learning this stuff, I hope. Okay. I expect you to be able to draw a circuit. You've had enough of your electrical stuff. And the fun thing is that the circuits in here are really simple. And along with that, I expect you to be able to predict current flow. That's kind of, excuse me, in electrical design, part of the way you know that you're done with your electrical design is if you can predict how much current's going to flow in the circuit. That means that you've got the right components in there, you've got power, you've got something to limit the current, you've got switches that's going the right way through, you can see it, and if you can predict the current flow, you're probably done with your analysis of the circuit for the most part. The hardest circuit that we have in here pretty much is an LED flashlight. And so if you think you could design, how many of you think you could design an LED flashlight? Okay, excellent, because that's the hardest circuit. And in fact, I wouldn't be surprised for 99% of you if that's the hardest circuit that you ever have to do. The trouble is the components in mechatronics, the components are all in different boxes. And that's the tricky part. I'll show you how to do it. But you're making an LED flashlight out of different boxes. All right. This may be a stretch, actually, because I think there's probably some of you that have had your transistor classes and some of you haven't. The good news is at the level that you need to use transistors here, they're switches. All you got to do is they're just switches that you got to make sure the current goes through the right way. And so they're easy. We can do that. But I'm going to expect you to do that. The mechatronics book that you could buy, for most of you, I wouldn't suggest that you buy it. I think it's a waste of money. You already have prerequisite books for lots of the things, the topics you're going to do that are way better. There really isn't a book. I thought about writing a book, but in today's world, writing a book isn't even what you really need to do to learn mechatronics. It's more of almost a YouTube kind of thing, or pretty much what we're doing, seminars or working on equipment. Okay, let's see. Obviously, I'm not going to provide you tools to do your wiring, so hopefully you got voltmeters and wire. And if you don't have that stuff, you're going to be doing your own wiring at home. I have some wire I can probably give you, but basically I expect you to have your own wire strippers and meters and whatnot. No oscilloscopes needed. You'll never need that. These circuits are too simple in mechatronics. Yes. Okay. I expect you to read drawings and understand tolerances. You guys have had tolerances, I presume, somewhere. Surprisingly, you haven't had to actually use them that much. I end up spending a huge amount of time dealing with the tolerances and numbers. And I'll point every time I can, I'll point out what I mean as we're going along. We'll have a couple times today when I'm talking about that. Let's see. I expect you to be able to program a microcontroller. And I think that's a pretty easy one for you guys. Let's get started on the first application. And we're going to spend about 40 minutes defining it. So to do that, I'm going to give you the experience that you would normally have. You're going to need to get a pen and paper out here, and you're going to take really good notes on this, because I'm going to write very little down on this. I'm going to be acting now like, not like your instructor, but I'm going to be acting like you're a customer or the guy from the marketing department, depending on, you know, the nature of the business relationship. But we're going to build a machine. You're going to need to build a machine. And in order to do that machine, you're going to need to gather information about it. So first, I'm going to kind of tell you a little bit about it, and then you're going to ask questions to further define what it is mechanically, electrically, how to make it work. Okay.